A sphere is a perfectly round geometrical object in three-dimensional space that is the surface of a completely round ball, like a circle, which geometrically is a two-dimensional object. A sphere is defined mathematically as the set of points that are all at the same distance r from a given point, but in three-dimensional space. This distance r is the radius of the ball, and the given point is the center of the mathematical ball. The longest straight line through the ball, connecting 2 points of the sphere, passes through the center and its length is thus twice the radius. It is the diameter of the ball. While outside mathematics the terms sphere and ball are sometimes used interchangeably, in mathematics a distinction is made between the sphere and the ball. The ball and the sphere share the same radius, diameter, and center. Terminology: pairs of points on a sphere that lie on a straight line through the sphere's center are called the antipodal points. A great circle is a circle on the sphere that has the same center and radius as the sphere and consequently divides it into two equal parts. The shortest distance along the surface between two distinct non-antipodal points on the surface is on the unique great circle that includes the 2 points. Equipped with the great circle distance, a great circle becomes the Riemannian circle. If a particular point on a sphere is designated as its north pole, then the corresponding antipodal point is called the south pole, and the equator is the great circle that is equidistant to them. Great circles through the 2 poles are called lines of longitude, and the line connecting the 2 poles is called the axis of rotation. Circles on the sphere that are parallel to the equator are lines of latitude. This terminology is also used for such approximately spheroidal astronomical bodies as the planet Earth. Hemisphere: any plane that includes the center of a sphere divides it into 2 equal hemispheres. Any 2 intersecting planes that include the center of a sphere subdivide the sphere into 4 lunar biangles, the vertices of which all coincide with the antipodal points lying on the line of intersection of the planes. The antipodal quotient of the sphere is the surface called the real projective plane, which can also be thought of as the northern hemisphere with antipodal points of the equator identified. The round hemisphere is conjectured to be the optimal filling of the Riemannian circle. The circles of intersection of any plane not intersecting the sphere's center and the sphere's surface are called spheric sections. Topology: in topology, an n-sphere is defined as a space homeomorphic to the boundary of a ball. Thus, it is homeomorphic to the Euclidean n-sphere, but perhaps lacking its metric. A zero-sphere is a pair of points with a discrete topology. A one-sphere is a circle, thus, for example, any knot is a one-sphere. A two-sphere is an ordinary sphere, thus, for example, any spheroid is a two-sphere. The n-sphere is denoted as n. It is an example of a compact topological manifold without boundary. A sphere need not be smooth. If it is smooth, it need not be diffeomorphic to the Euclidean sphere. The Heine-Borel theorem implies that a Euclidean n-sphere is compact. The sphere is the inverse image of a one-point set under the continuous function x. Therefore, the sphere is closed. Sn is also bounded, therefore it is compact. Remarkably, it is possible to turn an ordinary sphere inside out in a three-dimensional space with possible self-intersections but without creating any crease, in a process called sphereversion. Spherical geometry. The basic elements of Euclidean plane geometry are points and lines. On the sphere, points are defined in the usual sense. The analog of the line is the geodesic, which is a great circle. The defining characteristic of the latter is that the plane containing all its points also passes through the center of the sphere. Measuring by arc length shows that the shortest path between 2 points lying entirely on the sphere is a segment of the the great circle that includes the points. Many theorems from classical geometry hold true for spherical geometry as well, but not all do, because the sphere fails to satisfy some of classical geometry's postulates, including the parallel postulate. In spherical trigonometry, angles are defined between great circles. Thus, spherical trigonometry differs from ordinary trigonometry in many respects. For example, the sum of the interior angles of a spherical triangle exceeds 180 degrees. Also, any two similar spherical triangles are congruent. 11 properties of the sphere. In the book Geometry and the Imagination, David Hilbert and Stefan Cohn-Vossen describe 11 properties of the sphere and discuss whether these properties uniquely determine the sphere. Several properties hold for the plane, which can be thought of as a sphere with infinite radius. These properties are: the points on the sphere are all the same distance from a fixed point. Also, the ratio of the distance of its points from two fixed points is constant. The first part is the usual definition of the sphere and determines it uniquely. The second part can be easily deduced and follows a similar result of Apollonius of Perga for the circle. This second part also holds for the plane. The contours and plane sections of the sphere are circles. This property defines the sphere uniquely. The sphere has constant width and constant girth. The width of a surface is the distance between pairs of parallel tangent planes. Numerous other closed convex surfaces have constant width, for example the Meissner body. The girth of a surface is the circumference of the boundary of its orthogonal projection onto a plane. Each of these properties implies the other. All points of a sphere are umbilics. At any point on a surface, a normal direction is at right angles to the surface because the sphere. These are the lines radiating out from the center of the sphere. The intersection of a plane that contains the normal with the surface will form a curve that is called a normal section, and the curvature of this curve is the normal curvature. For most points on most surfaces, different sections will have different curvatures. The maximum and minimum values of these are called the principal curvatures. Any closed surface will have at least 4 points called umbilical points. At an umbilic, all the sectional curvatures are equal. In particular, the principal curvatures are equal. Umbilical points can be thought of as the points where the surface is closely approximated by a sphere. For the sphere, the curvatures of all normal sections are equal, so every point is an umbilic. The sphere and plane are the only surfaces with this property. The sphere does not have a surface of centers. For a given normal section exists a circle of curvature that equals the sectional curvature, is tangent to the surface, and the center lines of which lie along on the normal line. For example, the two centers corresponding to the maximum and minimum sectional curvatures are called the focal points, and the set of all such centers forms the focal surface. For most surfaces, the focal surface forms two sheets that are each a surface and meet at umbilical points. Several cases are special. For channel surfaces, one sheet forms a curve and the other sheet is a surface. For cones, cylinders, tori and cycloids, both sheets form curves. For the sphere, the center of every oscillating circle is at the center of the sphere and the focal surface forms a single point. This property is unique to the sphere. All geodesics of the sphere are closed curves. Geodesics are curves on a surface that give the shortest distance between 2 points. They are a generalization of the concept of a straight line in the plane. For the sphere, the geodesics are great circles. Many other surfaces share this property. Of all the solids having a given volume, the sphere is the one with the smallest surface area. Of all solids having a given surface area, the sphere is the one having the greatest volume. It follows from isoperimetric inequality. These properties define the sphere uniquely and can be seen in soap bubbles. A soap bubble will enclose a fixed volume, and surface tension minimizes its surface area for that volume. A freely floating soap bubble therefore approximates a sphere. The sphere has the smallest total mean curvature among all convex solids with a given surface area. The mean curvature is the average of the two principal curvatures, which is constant because the two principal curvatures are constant at all points of the sphere. The sphere has constant mean curvature. The sphere is the only embedded surface that lacks boundary or singularities with constant positive mean curvature. Other such immersed surfaces as minimal surfaces have constant mean curvature. The sphere has constant positive Gaussian curvature. Gaussian curvature is the product of the two principal curvatures. It is an intrinsic property that can be determined by measuring length and angles and is independent of how the surface is embedded in space. Hence, bending a surface will not alter the Gaussian curvature, and other surfaces with constant positive Gaussian curvature can be obtained by cutting a small slit in the sphere and bending it. All these other surfaces would have boundaries, and the sphere is the only surface that lacks a boundary with constant positive Gaussian curvature. The pseudosphere is an example of a surface with constant negative Gaussian curvature. The sphere is transformed into itself by a three-parameter family of rigid motions. Rotating around any axis, a unit sphere at the origin will map the sphere onto itself. Any rotation about a line through the origin can be expressed as a combination of rotations around the three-coordinate axis. Therefore, a three-parameter family of rotations exists such that each rotation transforms the sphere onto itself. This family is the rotation group, so the plane is the only other surface with a three-parameter family of transformations. Circular cylinders are the only surfaces with two-parameter families of rigid motions, and the surfaces of revolution and helicoids are the only surfaces with a one-parameter family. Cubes in relation to spheres. For every sphere there are multiple cuboids that may be inscribed within the sphere. The largest cuboid which can be inscribed within a sphere is a cube.